Recording in progress. All right, welcome everyone. August 17th, 2023. Get right into it here. I've got introduction and our general introduction and Stroud updates, and then Megan's going to talk to us about urban streams in southeastern PA. And then we'll probably have some time for discussion. Meeting is being recorded. All recordings are available here at the resources page. You can access that via this direct link, wikiwatershed.org/DRWI, or you can just go to the standard Wiki Watershed page, and there's a tab at the top that says DRWI, and that will get you there as well. Monthly meetings are every third Thursday of the month, 2:30 to 3:30-ish. It's the same Zoom link every time, so feel free to keep that for your records. I do send out reminders a week prior and then the day of, so please feel free to let me know if you have folks that would like to be on that distribution list. Send me email addresses. Our attendees of these meetings are generally from the Delaware Basin, groups associated with the Delaware River Watershed Initiative, and also just groups that are working in the Delaware Basin. We do have some folks attending from outside the DRB from time to time. The Stroud Center is currently supporting this monitoring work and facilitation and assistance work, EnviroDIY work with DRWI and CSAW, Consortium for Scientific Assistance to Watersheds. Four States, One Source is the DRWI website. It is a program that's much bigger than just this EnviroDIY stuff. And then CSAW is a PADEP funded program that allows the Stroud Center to provide support to groups in Pennsylvania without any, for free. So these meetings are basically just a time for us to kind of just check in and talk about, the general program monitoring and the DRB, EnviroDIY stuff, updates and such. And we usually have a presentation. Today it's going to be, as I mentioned, from Megan, it's going to be a nice science-oriented presentation about urban streams. Oh, man. Sorry, Rachel. So this is our team, David Bressler, me. Rachel is actually Rachel Leonard now, Krista Reeves and Shannon Hicks. Carol Armstrong and George Seeds, Master Watershed Stewards who are directly assisting the Stroud Center. There are others too that probably at this point I should have on there, such as Joe Debus. John Jackson, Matt Earhart, and Dave Arscott are the DRWI leads at the Stroud Center. Our primary goal from the Stroud Center perspective on this work is to support station owners, managers, and volunteers in using these EnviroDIY stations, as well as just overall monitoring for their own kind of local watershed purposes. Secondarily, we are certainly looking at the data from the continuous stations as well as other monitoring data and helping to support understanding the data, developing tools to communicate the data and understand the data. So I'm just going to go into updates from the Stroud Center on all this stuff. Rachel Leonard, formerly Rachel Johnson. Rachel was recently married. She is no longer, we announced this last month, but this is the last month now that Rachel is going to be officially involved with this particular work. So, but she is still going to be with the Stroud Center. She's just going to be working on a master's degree associated with University of Delaware. And she's going to be doing that with Mark Papak, who's a researcher at the Stroud Center. I have a link here to take to this article that was published on the Stroud website about Rachel's background and where she's going. So congratulations to Rachel, and hopefully she'll finish her graduate degree and be able to come back and work with us again. So Shannon Hicks, reintroducing Shannon to everyone who most people know of Shannon, but she kind of just stays semi under the radar and just gets the work done. But Shannon is going to continue to be the main technical field person for technical support, field support, assistance in the field, as well as assisting via email. And Shannon is one of the main supports on the EnviroDIY.org forum. And Shannon is the main engineer at the Stroud Center, and she is the inventor of the MAFI data logger and the EnviroDIY continuous stations. S. Hicks at stroudcenter.org. Along those lines of Shannon's support, we would greatly appreciate if you do need support on your stations that you fill out a service request form. It's a very simple form. You can go to this general resources page, and it's at the top of that page. You just click this button and fill out a few required components of that. Very basic. And then there's other other information that you can fill out if you want, which is appreciated but not necessary, that gives a little more information about your situation. Again, just as a reminder, anytime you visit a station, it's very helpful for just general proper record keeping, to fill out a data form. You can do a hard copy, which you can access on this web page. You can print those out if you want, or you can just fill them out online. But always we ask that you, even if you do fill out a hard copy, enter it into the online form so that it's there and stored nicely. There's basically the same idea. You can print this hard copy form out and then enter it into this online Google form. Just as one more just general sort of note, lots of other guidance materials at this website. There are shortcuts to different sections, but there's a long list of different products there, help resources, recordings of our past monthly meetings, past presentations, so on and so forth. Also wanted to mention, there's quite a few groups that are doing these synoptic sampling events, aka snapshots or blitzes. Lots of people doing salt snapshots, a few groups starting to do temperature snapshots. So please feel free to be in touch if you are considering doing this or would like support in doing one. And just one last thing, if you have, if you want, you can certainly feel free to send Diane and or me, photos from your work, stories about your work, what you're up to, successes, challenges, learning experiences, whatever, and Diane can amplify those on Stroud's social media platforms. Wanted to also mention next month's presentation on September 21st is going to be by John Jackson. It's 2 months of presentations. John's going to be talking about the science of salt pollution and recent advances. And then in October, I'm going to follow up with monitoring of salt and, communicating that information at the local level. I'll be doing that in association with the local policy and practice work group. So here's that. Next month, John, next month, me. We're going to have student presentations in November. So if anyone has, some all-star high school or college students that you're working with that are doing some kind of good independent study type work, feel free to put them in touch with us, I guess with me directly. And we can think about whether they're up for doing a 5 to 10 minute presentation in November. And then December is going to be a kind of year-end review, and I'll do that. But certainly if others would like to participate in that, please let me know. I'm happy to pass off presentations to other people. And again, just as a future note, December 14th, the meeting is going to be. December 21 seems too close to the holidays, so we're going to move it to the 14th of December. I will pass it off to Ian right now. Ian, if you want to, I can just advance the slides myself.
I think that would probably be easiest at this point. We only have a couple of slides, so
sounds good.
Here with our monthly update on the local policy practice work group. Things are going great there. Current leadership, we continue to have our meetings on the first Thursday of every month from 11 to 12:30. If you or anyone you know would be interested in this, feel free to send me an email, which is ian@njhighlandscoalition.org, or send an email to Dave, and we appreciate any and all input on this. So, Dave, if you could advance the slide. Our short-term charge remains the same, which is to develop the most effective way of employing stream monitoring data, which is our conductivity, temperature, depth, and turbidity, as it relates to advising the municipal entities on various components of their policy. And to that end, Dave, if you could advance. We've made some great progress with our temperature and our municipal interactions documents. For the temperature, we are in internal review right now with that. So everyone who is a part of the local policy practice work group, we have been doing edits almost nonstop the past couple of days on both document 5 and the putting stream temperature data to work documents. We're excited to say that the municipal engagement document, aka document 5, is moving on to external review, which means that we are consulting people outside of our group to get their feedback on it. Dave, if you could advance. We have some consulting local leaders, the first of whom we're going to be reaching out to tomorrow, which is Beth Uller, who is the PA Center for Watershed Protection. And then after that, we are going to be reaching out to Ross Snook, and we will have additional eyes through other contacts that they have, as well as our own contacts, such as Betsy, Eileen, and Susan, who we look forward to hearing their feedback from. Once the external process is done, then we'll come back as a group, figure out the next steps after that. But hopefully it'll then be a living document that we can start sharing. But for now, that is where we are, and we're making some great progress with that.
Indeed. Thank you, Ian. Okay. Any questions before we pass it off to our presenter for the day, Megan? Any questions? Any questions on your part? Right? Urban Stream Syndrome in Southeastern PA, Megan Fork from Westchester University. I will stop share and let Megan take over the share.
Cool. All right, I will start share. And then I'll put my thing in presentation mode so that you see slides full screen. Hopefully you see a slide full screen right now.
Yep.
Excellent. Okay, so great. So I'm going to talk a little bit about the urban stream syndrome, and I'm going to use an example from in the Delaware Basin, in the headwaters here of Chester Creek, marked by the little yellow star just here, just to give some examples, like some on-the-ground observations. And when we're talking about urbanization, one of the ways that we quantify that is using the amount of impervious surface. So that's like roads and sidewalks and roofs, anything that doesn't let water infiltrate into the ground. We use that percent impervious cover in the watershed as one way to quantify our measure of urbanization. How urbanized is the watershed? And so what you'll see in this map here is that Philly and its suburbs, especially along the lower parts of the Delaware River here, have really high percent impervious surface, indicating that there's a lot of development in those watersheds. And before I really jump into the data here, I would like to start by acknowledging, this is not just me working alone. I had a lot of student researchers here at Westchester, both in classes and independent graduate and undergraduate students working on this. And then I'm going to talk a little bit about some previous work from Baltimore, just a little bit south of here, to illustrate some other pieces. And in that work, I had some collaborators and co-authors, as well as some help from people at the Baltimore Ecosystem Study and the Cary Institute of Ecosystem Studies. So, great. So the urban stream syndrome. This is a term that we use to describe this set of symptoms that are common across streams in urbanized landscapes kind of throughout the world. And this is a term that was coined almost 20 years ago in 2005 by Walsh and others. And they were they used this term to really summarize a body of research, that concerted research on urban streams that really started in the mid to late 90s. And so they were in this paper that they published in 2005, they were really summarizing these observations about urban streams that happened in the previous 10 years or so. And what they described is in this table from that paper, they described several kind of consistent responses that we see in urban streams across these various sort of types of data. So consistent changes in the hydrology, the water chemistry, the channel morphology of these systems, as well as some of the more biological things like the amount of organic matter and the way it behaves, the organisms living in those streams, and the ecosystem processes. And I will not dwell on this table too long. There's a lot of stuff in here. I'm going to focus on these highlighted things here. And I'm using yellow here to show some symptoms that we can look at using sort of the data that we get from the CTD sensors that many of us are using. And I'm going to talk a little bit in blue about some other symptoms that we can measure, kind of complementary to those high frequency sensor data. And to do that, I'm going to use Goose Creek as an example. It's highlighted here in the sort of shadowed and slightly darker blue here in the headwaters of the Chester Creek watershed. And I'm just going to talk through a few of these symptoms, and then I'll show you data from Goose Creek as an example of how these symptoms manifest. So to start, a consistent change or a consistent symptom of the urban stream syndrome that we see is these large and rapid changes in flow during storms. And as a shorthand, we'll say flashy hydrology for that. And this is really driven by that impervious surface. So in these two little cartoons, we're looking at sort of when rain falls on a landscape, what happens to it? What is its fate? And on the left, we're looking at an undeveloped watershed. We see about 40% of that rain go back into the atmosphere, and about 10% of it runs off. The rest of it infiltrates into the ground. And when we start laying down impervious surface as part of our development, we see a lot less of that that runoff go, or that rainfall go into infiltration because it's blocked by that impervious surface. And so more of that rain runs off the landscape and directly into streams. So that's the ultimate cause of this flashy hydrology. And you can see that in our water depth data. So here are some data from a storm earlier this summer in the middle of June. We had a big thunderstorm, almost 2 inches of rain, and we can see in Goose Creek, we can see the water depth increase from just about a foot to about 4 feet. And at the highest rate of change, the stream level is going up about 1 inch per minute. So this is so quick that you can stand there in the stream and you can watch the water rise. It's basically a flash flood. And just so you think I'm not like cherry picking a storm or anything, I want to compare that to a more rural stream. So here we're looking at the same day, the same storm, just a bit south near Longwood Gardens. So I just picked another EnviroDIY sensor to pull the data from. And what I hope you'll notice here is that even though we have about half as much rain, that, that's just the nature of the beast, but we see much less than half the magnitude of peak flow, as well as much more gradual changes in the depth. So when we talk about this flashy hydrology associated with the urban stream syndrome, we're talking not only about the peak being higher, but about those changes being more rapid. And the consequence of this flashy hydrology at this specific point in Goose Creek is that so this is pictures. My poor spouse, every time it rains in this watershed, I'm like, get on your boots, we're going out to take pictures. And so these are some photos that I took during that rainstorm. And so just about any time we get an inch or more of rain, we see this stream overtop its banks and start flowing down the street and into the park here. So, and this is, I think we all know from the past few years and the hurricanes that we've seen that this is really common in a lot of urban areas in this, in southeastern Pennsylvania, certainly. And one of the consequences of all of this flashy, quick, big changes in stream flow is erosion of the channel. And so when we start to urbanize a landscape, we're starting with a stream that's in equilibrium. So the amount and types of sediment that make up the bank of that stream is in equilibrium with the flow regime of that stream. So the sizes and frequency of floods. But when we start to add impervious surface, route more of that water into the stream, we get this typical pattern in erosion where we first start to see incision of that stream channel. So it gets deeper, and then it starts to get wider and threaten the infrastructure and the trees and the buildings and all of that are around the stream. And so this is one example of a stream channel cross section from Goose Creek showing that incision, those really steep banks with the stream kind of low in that channel. There's a lot of steep exposed bank above that channel because of that incision of the stream. And this one cross section that I'm showing you is not just this one position in the stream. We actually see, there we go, this erosion in many places throughout the stream channel. So here we're getting erosion that is threatening to bring down this fence into the stream, and you can start to see some of the slumping of the bank here adjacent to this building. So we keep getting these floods, we're going to keep eroding this stream bank and threatening this infrastructure, as well as these trees here. And last summer, we had a student walk the length of the channel from the headwaters down to 202 and map these erosion features. And so you can, each of these orange dots along the channel is one of these major erosion features. So he took photos and cataloged the locations of all of these places to demonstrate that we've got, you know, this major feature or the symptom of the urban stream syndrome present throughout this stream network. One of the other symptoms of the urban stream syndrome that we can characterize with the CTD sensors is changes in water temperature. And so this image from the USGS here, we're looking across a landscape from rural at each sides to kind of from suburban and into downtowns. And then in the blue and red and orange, we're looking at the temperatures. And so what this image is trying to show us is this urban heat island effect. And this is really especially present during the night. So urban centers tend to stay warmer than their rural counterparts, where other places where, you know, like the rural and suburban areas will cool off at night. We see a lot less of that cooling off in the downtowns. And the other thing I want to point out here is our water features. So water holds heat a lot longer than air. And so what that means is our urban streams are holding a lot of heat from these heat islands and staying warmer at night than they would in rural areas. And it's not just this consistent like effect over time of the heat island, not just this day to night differences that are exacerbating long-term warming of the climate, but we also see these really short-term changes in water temperature that I'll term flashy water temperature. Just like we saw these really rapid changes in the depth of the stream, we can see these really rapid changes in the stream temperature. And so here we're looking at the temperature data from this Goose Creek sensor. And this one is just this past weekend, Saturday. So Saturday afternoon, this past weekend. And we see at 4 o'clock in the afternoon, the stream temperature change almost 4 degrees over a really short period of time, as we have a storm, and it was a really hot day, and that storm water hits that hot pavement and then is routed directly into the stream. And so if you think about what the organisms living in this stream have to deal with, they have to be prepared for this like really quick change of almost 4 degrees, which doesn't sound like a lot to us, but if you think about the difference of setting your thermostat 4 degrees and how different your level of comfort is depending on that, and then think about changing that, you know, in just a matter of minutes. This is something that a lot of these organisms are not adapted to, is these really rapid changes in temperature, because they are used to living in water which holds temperature fairly well. And so again, we can compare this behavior in Goose Creek to a more rural example, and you'll see that during this same storm, we see a slight change, a slight uptick, and then decrease in the temperature, but not nearly of the same magnitude that we see in our urban stream. So we've talked a little bit about the flashy hydrology. We've talked a little bit about how that drives erosion in our bed and bank. We've talked about these high and flashy water temperatures. And now I want to kind of move into talking about pollution as part of the urban stream syndrome. So I'm going to start by talking about salt. And I'm going to breeze pretty quick through this because I know that many of us are well acquainted with conductivity, and you're going to have 2 more talks about conductivity. So yeah, I'll be brief here. So here we're looking at last summer average temperatures from a little bit of synoptic sampling, as well as the spot measurements that we took when we were out visiting the sensor. And so we averaged, just at this site, we averaged just over conductivity of just over 1200 microsiemens per centimeter, well above the recommended range. And so these are the base flow measurements during the summer. And so we can see that the long-term accumulation of salt in the groundwater means we have these elevated conductivities that we're all seeing in salt snapshots probably throughout our watersheds. And then, of course, the other problem that we see is these big spikes in conductivity during winter rainstorms, where we've applied salt in anticipation of snow or sleet, and what we actually got was rain that just washed all that salt directly into the groundwater and into the stream. So here we're seeing, this is some data from winter 2022 showing those big spikes in salt concentrations associated with those winter rainstorms. Now I'll move on to some of the things that are beyond our CTD sensor data. One of the another issue that we see commonly in urban streams is elevated concentrations of nutrients. And so Goose Creek also has this problem. We have high concentrations of phosphorus, and this can lead to eutrophication and algal blooms, which in turn can lead to like poor quality biotic communities, really not diverse, missing a lot of the key organisms, as well as fish kills and things like that, as that algae is decomposed and uses up the oxygen in the water. And indeed, the EPA has listed Goose Creek as an impaired water because it has phosphorus concentrations well above the limits. And just from last summer, we measured reactive phosphorus. The standards are based on total phosphorus, so all of the phosphorus that is in organic matter, as well as free in the dissolved in the water. We measured just the reactive phosphorus, so a subset of that total phosphorus, and we still measured concentrations more than 2.5 times in excess of the recommendation. So, we have a nutrient problem here in Goose Creek, like in many types of urban streams. I also wanted to take a moment to talk about contaminants of emerging concern, or what we call emerging contaminants. So these are things like, well, I'll just move on to my definition. So these are, when we talk about contaminants of emerging concern or emerging contaminants, we're really talking about a set of chemicals that are not commonly monitored and for which we don't have any kind of clear regulation usually, but are known or are likely to affect human or ecological health. And so these are not chemicals that are like related in any way other than the fact that they're not monitored and have health effects. So these can be things like flame retardants, pharmaceuticals and personal care products, nanomaterials, algal toxins from harmful algal blooms, industrial chemicals like PFAS. So we've had a lot of PFAS news recently, pesticides, and microplastics. So these are a bunch of different unrelated chemicals, and that is in part what makes them so hard to monitor in sort of a concerted and regular way. And I could talk about, if we were going to talk about all of these, we'd be here all day. So I'm just going to talk about pharmaceuticals for the rest of the talk here. And one of the things, or a couple of the things that we should know about pharmaceuticals in the environment, one of the reasons that I think they're interesting to look at is that they are designed to work at really low concentrations. They're designed to have some kind of biological effect at very low concentrations in animal bodies. So what that means is that when they get into the environment, they can disrupt the physiology of animals and ecological processes, even when they're at very, very low concentrations, like concentrations that if we were measuring salt, we would say that is no problem at all, but these are biologically active at these really low concentrations. And the other thing I would like you to know about pharmaceuticals in the environment is that most of these studies have been done just downstream of wastewater treatment plants because these are well-known sources of pharmaceuticals. And that's in part because our water treatment process is not currently designed to remove these things. Our water treatment plants do an excellent job of removing nutrients for the most part, and especially removing bacteria and things that can make us sick. They do a great job of the job that they are designed for, but they are simply not designed to remove pharmaceutical pollution because this is a relatively new problem. So that said, one of the questions that I wanted to answer in the research I'll talk about is, do urban watersheds, even upstream or that don't have wastewater treatment plants, do we still see pharmaceutical pollution? We know that we have an aging infrastructure problem in our country. A lot of our, especially our subsurface water infrastructure is getting pretty old, getting pretty beat up. And so we might expect that there are leaks of sewage underneath the ground in our urban watersheds that may be contributing pharmaceutical pollution. And so we wanted to assess whether or not that was the case. And we also wanted to ask if there are patterns or predictors in pharmaceutical pollution, because these samples are very expensive to run. We're talking about hundreds of dollars for one water sample. And so if we can find ways to predict or to have some kind of proxy for pharmaceutical pollution, then we can address whether any solutions that we try to implement are helping to solve the problem without having to spend buku bucks to do it. And so here I'm going to ask you to travel a little bit south to Baltimore. So here, right here is the downtown, like inner harbor of Baltimore. And we're working in this watershed that spans from pretty dense urban Baltimore upstream into the suburban. And then we also have some low density watersheds with no people in them or very sparse, like ex-urban. And so we're going to compare across these watersheds and we're going to look over time. And an important thing to notice here, I mentioned that thing about wastewater treatment plants. So sorry, I was putting my cursor on the wrong screen. This whole watershed here is on a centralized city sewer, but there is no wastewater treatment plant in this watershed. So all of the sewage from this watershed is piped across the watershed boundary and treated in a water treatment plant either here or here. So no wastewater treatment plant effluent. So the only potential source or the main potential source of pharmaceuticals we expect is from leakage of that sewer infrastructure. And so to get at this problem, we used a year of weekly water samples. So at each of the yellow triangles in this figure, we collected water samples every week for a year. And then we screened for 92 different pharmaceutical compounds in each of those samples. And we also had stream flow data. So similar to the depth sensors that we have on the EnviroDIY, we just use the USGS network that is already in place here. And so the first thing I want to look at here is the pattern of pharmaceutical concentrations across space. So earlier in the talk, I introduced measuring urbanization by impervious surface. And here I'm measuring urbanization by population density in the watershed. So how many people per square kilometer are living in this watershed? And I've organized the sites here from no people or very few people to really dense urban watershed. And one of the patterns that sticks out to me here is that as we go from low to high population density, we start to see more different kinds of pharmaceuticals popping up in our samples, and we start to see a higher percentage of those samples showing detections of these kinds of things. So more different kinds of pharmaceuticals and more samples with pharmaceuticals in them as we get more urban. Oh, good heavens. Okay. And here are similar data organized in the same way from low to high population density. And here we're looking at the concentration. So the top of this stacked bar is showing the total concentration of pharmaceuticals, and then the color is indicating which type of pharmaceutical. And these black dots are showing our population density. So again, we're seeing this general pattern of the more dense our population is, the more urban our site is, the higher concentration of pharmaceuticals we see over the course of this year. Now I want to talk about these patterns over time and start to look for some predictors of pharmaceuticals. And to do that, we're going to zoom in on the watershed outlet. So down here where this watershed, pretty close to where this watershed goes into the Chesapeake Bay. So kind of summarizing all the stuff that's happening across this rural to urban gradient. And this relatively busy figure is showing us the patterns in concentration over the year. So I'm going to mostly direct our attention first to this one in the upper left. So here we're showing, this is kind of the same data that made up those stacked bars of different colors. Each of these dots is showing the total concentration. So we just added for all of the different pharmaceuticals that we detected, we just added their concentrations, and I'm showing you the total concentration over the year. And so what we're really, we're seeing a pretty stochastic, by which I mean there's not really coherent patterns over this year, and we're not seeing things being really consistently higher in any point in the year. We can see these zero concentrations, so times when we didn't detect pharmaceuticals at different times throughout the year. And then when we start to break these data down and look at different types of pharmaceuticals, what we start to see is that they are not behaving coherently with one another. It's not like there are certain times when we're seeing, all the different pharmaceuticals showing up and then disappearing. They're really kind of each blinking in and out independently of one another. So no coherent patterns over time, or no, not really any evidence that different types of pharmaceuticals are pairing up or showing up together. And the other thing I want to point out here is that we are talking about very low concentrations. So just about 120. So our concentration is measured in nanograms per liter. So that is 3 orders of magnitude less than micrograms per liter. If you're thinking about when we're looking at salt in milligrams per liter, or 6 orders of magnitude less than that. So like a millionth of the concentrations of salt. Or in other words, when we see samples at about 120 nanograms per liter, that's more or less the equivalent of a healthy pinch of salt in an Olympic-sized swimming pool. So really dilute. But as you know, like even though this is really dilute compared to some of the other kinds of toxicants that we're interested in, again, these are designed to have biological effects at really low concentrations. And indeed, we've seen biological effects at environmentally relevant concentrations like this. And I'm not going to talk about those at this point. in the interest of time. But this is part of the reason that, like, I think it's just mind-boggling that we're able to detect things at these really low concentrations. And that's part of the reason that these samples are so expensive to analyze, because in order to get kind of meaningful data, we need to be able to resolve these really low concentrations. So our instruments are like really, really doing impressive work to get us these data. So when we're looking for patterns or ways that we might be able to predict these pharmaceutical concentrations that we know are having impacts on our streams, one of the first things we might look to is to see whether there are patterns with stream flow. And this figure is really showing us we're not seeing really coherent, we're not seeing a pattern that indicates that these things are being diluted when there's a lot of flow in the stream, nor are we seeing a pattern that would indicate that these things are being transported to the stream during storms at high flow. And that is in contrast with nutrients. So here we're looking at some total nitrogen data in red. And so this figure, we see this pattern where nitrogen concentrations are more dilute at high flow. So they're being diluted as rainwater comes in. And in contrast to that, when we look at total phosphorus in blue, we see total phosphorus tends to be higher at high flows. And that is indicating that as these flows are moving phosphorus from the landscape into the stream. And so, this was kind of our first cut, like maybe we'll be able to see some pattern with stream flow in the way that we do with nutrients. Clearly that didn't work. So we brought in the big guns to use a machine learning process to see if we could take our whole suite of observations. So all of the kind of conductivity, stream flow, different other water quality aspects that were part of our routine sampling to see if we are able to predict pharmaceutical pollution and nutrient pollution. And what we see when we apply these random forest models, which is a type of machine learning, we can do pretty well for nitrate and total phosphorus. We have error rates less than 10% for both of those nutrients. So we can do a pretty good job of predicting when total phosphorus is at high versus low concentrations, but we're not able to do the same for pharmaceuticals. So when we pick one specific pharmaceutical, this is trimethoprim is a type of antibiotic, and it was actually the single pharmaceutical that we detected most often in our samples. And here, so basically, like if it's above the threshold that our instrument can detect, it'll mark as as present. If it's below that threshold or truly absent, we'll record it as absent. And here we have an error rate of 33, almost 34%. So the same kind of methodology that we use to predict nutrients cannot predict pharmaceuticals. And this was a little surprising to us because we thought that, if these things are coming from leaks in sewage, then nutrients and pharmaceuticals should be traveling together into the stream, but that does not appear to be the case. So we don't have something kind of an unfortunate conclusion to take away from this is that we know that the pharmaceuticals are there. We know that they are causing ecological problems. They're changing the physiology of animals. They're altering the rates of organic matter processing by organisms in the streams, but we don't have an easy tracer or an indicator for emerging contaminants like pharmaceuticals. However, we do see, like when we look across space, we tend to see that there are more of these at high concentrations in urbanized streams as compared to rural streams. So that is sort of the end of the data that I want to talk about. However, I do want to put in a plug for if you are interested in learning more about urban streams and the research going on at urban streams, and if you need to watch some more webinars in your life, the Symposium for Urbanization and Stream Ecology has a webinar series that runs just about monthly, every month or 2 months for the academic year. So we'll be starting those up again in September. And you can go to urbanstreamecology.org to join the mailing list and to find publications and all sorts of stuff if you want to learn more. And I do not want to leave you with just kind of the story of woe. So I do want to point out that there are things that we can do to help mitigate the effects of our urban footprint on the streams that drain our landscapes. And for our approach to kind of flooding and erosion is really about slowing down stormwater and letting it soak into the ground. And so we can do that through things like rain gardens and bioswales, floodplain restoration and things like that that help water interact with the landscape, infiltrate into the ground, and not race directly over impervious surface and through pipes into the stream. And when we're talking about salt and nutrients, again, I think I'm a little bit preaching to the choir here, but we can reduce the application of salt and fertilizers. We can clean up our yard and organic waste, and we can be smart about when we're applying these things, not right before rainstorms, to help decrease the amount of salt and nutrients getting into our streams. And then lastly, I want to talk about the fact that a lot of these, the streams that are suffering the most from urban stream syndrome are oftentimes found in communities that have been historically disinvested in and things like that. So we need to think about simultaneously bringing restoration to that community as well as to that landscape. And I think that watershed organizations like the Goose Creek Alliance and the Goose Creek Watershed and all of your watershed organizations are the institutions best positioned to think about and do this work. So I will end there and would love to chat with y'all about this.
Awesome. Thank you, Megan.
Can I ask a question now?
Go for it, Pete. I sense you're chomping at the bit.
Well, not completely, but it was a great presentation, great work. I do have a question though. Was there any thought to looking at the distance between where the various pharmaceuticals are made and the streams that contain these pharmaceuticals?
Yeah, so we so in Baltimore, I do not have information about pharmaceutical manufacturers. And I mean, I think here in the Delaware watershed, that would be a lot more, we know that we have a really big pharmaceutical industry here. So we thought about kind of trying to get information about pharmaceutical manufacture and about hospitals, where we would expect pharmaceuticals to be used a lot more than maybe the rest of the urban landscape. We don't have access to that information about like where these places are located in a reliable way. So we haven't done that. But I mean, I think one of the interesting things that these data show as well is that, if these things are being released by these, in kind of point sources, they're not being diluted in the way that we would expect a point source to be diluted at high flows. And they're not being consistently released because we see these samples with zero detection kind of across the year at various points. So I think I think that would be a really interesting kind of further application of this research, but not one that we took on as part of this.
Thanks. It'd be interesting to know exactly how the pharmaceutical companies are disposing of any of the drugs that have maybe lapsed or that are left over from the batches that they're making.
Yeah, absolutely. I mean, I think certainly those are regulated by, Clean Water Act and hazardous materials legislation and stuff like that. And, you know, just like with anything, whether those regulations are being followed, we can't say. But I think my expectation is that a lot of that would be routed through like hazardous waste pickup. But again, like, I'm not sure. And I think
Yeah,
that's
and
a really
they just
interesting
hire
question.
somebody who happens to have a license to do that. And maybe the driver takes a shortcut to the Susquehanna and dumps it there or something. You know, who knows?
Yeah.
Thank you.
Kim. Hand raised.
Yeah, thanks, Megan, for a great presentation. I wanted to ask, I was curious about, you showed some data that pertaining to the nutrients that showed nitrogen showing a dilution effect during a storm and the phosphorus level increasing because it was running off from adjacent land surfaces. I was just curious, is that particular to Goose Creek, or why do we see that happening with phosphorus but not nitrogen?
Yeah, that's a great question. So those data were actually from Baltimore, but the nitrogen dilution is not something that is consistent everywhere. So sometimes we see we'll sometimes see nitrogen behaving in what we call a chemostatic way, where the concentrations are pretty similar across stream flow conditions, or sometimes we'll see that dilution. Phosphorus, we almost always see that increase at high flows. And part of the reason for that is because most phosphorus is coming in either as particulate or associated with particulate matter. So in the same way that, like, when you are looking at a stream and it gets like cloudy or like milky at high flows, that's because sediment is being transported into the stream, and a lot of the phosphorus is being transported either like stuck onto that sediment or as part of that sediment. And part of the reason for that is because phosphate, which a lot of the phosphorus is in the form of phosphate, has a -3 charge. So it's really sticky. It wants to stick to something because of that really strong negative charge. And so that means it sticks to clay particles and sediment particles and stuff like that.
Awesome, thank you.
Phosphorus sticks, nitrogen doesn't, right, Megan?
Yep.
Carol.
Thanks. Yeah, that is consistent with the presentation we just saw at NASA in their development program, where when they the National Park Service in the upper Potomac River Basin was looking at land cover land use and what it might correlate with. And yeah, they didn't find correlations with nitrogen, but they found strong correlations with phosphorus and deforestation. So but that's not what my question's about. So, you know, you pointed out in the beginning that, so first of all, thank you for this absolutely fascinating presentation. And you pointed out in the beginning that aquatic life is very sensitive to a lot of these contaminants. And I think that there's growing interest in the impacts of the ones that we'll stick with pharmaceuticals, impacts of pharmaceuticals on aquatic life. But I was wondering if you had thought about including endocrine disruptor medications in your analyses, because we know what the impact of that is on aquatic life. It causes them to be sexually dimorphic, if that's the right term. So that's one question I'd be really interested in your thoughts on. And I'm just going to throw out my other question now too, which is that since Pennsylvania passed the fertilizer law in, I think, 2022, is there any expectation, or is anyone going to study if it might decrease the fertilizer runoff?
Yeah, a couple of great questions. So we did have an not necessarily an endocrine disruptor, but a pharmaceutical that acts on the endocrine system on testosterone. I cannot remember the name, like with a list of 92 pharmaceuticals, I cannot remember all of their names. So you'll have to forgive me there. And I can definitely send you a link to the manuscript if you want to look more into that. So we do have those in our data set, but really we were just kind of working with like our goal was to characterize these broad patterns. So there's really cool studies in California and in the UK zooming in on specific pharmaceuticals and specific impacts. Another thing I will point out is there are really interesting studies looking at some psychoactive pharmaceuticals, so medications for like depression and anxiety, showing changes in behavior of fish and crayfish, which, you know, can cascade into ecological effects. So there's a study by a collaborator in Florida that looked at behavior changes in crayfish, showing that in like the presence of some of these pharmaceuticals, the crayfish were more likely to act in a bold way, which makes them more likely to be predated on by predators, which changes the way that energy and contaminants flow through the food web and stuff like that. So there's a lot of really interesting research on individual chemicals or individual pharmaceuticals and what that means for at the ecosystem level and the food chain level. As for the question about the fertilizer ban and farm nutrient levels in streams, I would be shocked if someone is not looking at that. I'm sure that someone is. I am not involved in that work, but I would bet that at least certainly in the Chesapeake Bay watershed, you know, someone's measuring that. And if not DEP, then, you know, like other folks. And I think it'll probably be a couple of years before we see anything come out about that, but I'm sure that that is being monitored.
And quick question about SUSC, Suze, how do you pronounce it?
Oh yeah,
Suze?
yes. Some people involved say Suze and some people say Susie, so you're fine either way.
Either way. So I did see one webinar. Since I wasn't familiar with the organization, I a little thrown off when I saw it was associated with Australia. So I wasn't sure if the research, urban research, was how much of it was relevant to the United States or.
Yeah, so it is. So it's an international organization. We've got research from so that Walsh and others that coined the term urban stream syndrome. That is a research group out of Australia. But again, like that paper was really summarizing urban research throughout the world. So these urban stream syndrome patterns are things that we see here. We see them in Australia. We see them in urban streams no matter where we look in the world. And so the presentation that you saw had a lot of people from Australia, but we've had folks from the UK. We've had folks from so it depends any given month where the person is coming from, but it is international group.
Thanks.
Okay, we are at 3:37. Are there any other kind of relatively quick but pressing questions from anyone? All right. I'm going to stop recording, or actually, well, yeah, we're past time. I'm going to stop recording though. Stopping recording.